Okay, in this video we're going to be talking about page 9 of note 7 of Calc D. We're talking about double integrals, and what we're going to talk about in this one is how sometimes changing the order of integration is actually necessary. Sometimes you can only do a problem using one order of operations or order of integration. And if you watched all of the last video, you realized even though sometimes you can do it both ways, one choice may be significantly better than the other, as I demonstrated by taking 7 minutes for one of them and then like 20 minutes for the other. So let's take a look at an example where this is the case. So we want to integrate over the region R, which will be described, e to the y squared dA. R is the region in quadrant 1 bounded by y equals x over 2 and y equals 2. It's going to be a triangle. So let's look at that. So this is our region. And here is the problem. If we try to integrate e to the y squared dy, we can't. We don't know how to do it, right? You would try to take u equals y squared. That means you would need 2y dy. We don't have a y, and you can't multiply one in. So we can't do it. And since you can't do that, it is not possible that the y bound should be the first integral. So they're going to have to be the constants, right? So within this region, if you look at it, the y values just go from 0 to 2. If we let y go from 0 to 2, we just have to figure out what's happening with x. And so y is going to go 0 to 2. And now originally we have y equals x over 2, but we're just going to change that up and say that x is 2y, and x always wants to go from left to right. The left curve is 0, and then the right curve is x equals 2y. So it goes from x equals 0 to x equals 2y, moving from left to right. So those are our bounds. All right, so we can now just write this integral and do it. So we're going from 0 to 2, we're going from 0 to 2y, e to the y squared, dx, dy. We're doing dx first because when we integrate that, it'll just give us an x, and then we can plug in 2y and plug in 0. We could not have done e to the y squared dy dx because we'd have no first step. There's nothing we could do. That's why we're changing the order. All right, this is, I think, straightforward. So 0 to 2. We're going to pick up an x when we integrate with respect to x, and then x is going from 0 to 2y. When I plug in 2y, I'm just going to get 2y, and when I plug in 0, I get 0, so we're actually just going to get 0 to 2, e to the y squared, quantity 2y minus 0, but just 2y dy. That's perfect, so we can just integrate that. If you're doing, they always end up being like, straightforward integrals. So the integral of 2y e to the y squared is just e to the y squared, going from y equals, I always write y equals because I'm just so used to it being the inner bounds. At this point, you don't really need to do that because there's only one variable, but it's okay. When I plug in 2, I'm going to get e to the 4th. When I plug in 0, I'm going to get e to the 0, which is not 0, so keep that in mind. Plugging in 0 doesn't always zero out the thing. Sometimes it gives you 1. It usually gives you 1 if it doesn't zero it out, actually, but you still need to think about it. That's our answer. All right, we are going to look at another one. All right, so we are going from 1 to 9, from root y to 3, x e to the y dx dy. So what we want to do, this actually, you can do this one the way that it's given, I'm pretty sure, but it's, again, not the right choice because it's going to involve integration by parts, and we don't want to do that again. So what I'm going to do is I'm going to pull the inequalities off the bounds, and then I'm going to sketch the region, and then I'm going to reverse the order of integration and evaluate it. That's my plan. So pulling the bounds off, we can tell that the x bounds, it's a little easier because I'm color coding it, but it's always like the inner differential goes with the inner integral, the outer differential goes with the outer one. Although, I mean, if you're into it and you have enough colors, color coding is definitely the way to go. And then y goes from 1 to 9. All right, so we're going to want to reverse the order of integration. Also, we want to sketch the region. So here's a problem that I sometimes have. I don't really know what x equals root y looks like. I mean, I do, but like, what if it was more complicated? So what I will do is I'll just always take these bounds and, rearrange them. So y is x squared, right? But we only want part of it. We only want like I guess like the right half of it, you might say, because x has to be a positive. So this is our region, and through this region, x is going from 1 to 3, and then y is going from 1 up to the curve, so going up to x squared. That's what we're doing. X likes to go from left to right, y likes to go from bottom to top. So let's reverse the order of integration, and evaluate. So we're going to try to do dy dx. So as we said, x is going from 1 to 3, from left to right. That keeps you within the region. If you try to go 1/2 to 3, between 1/2 and 1, you're not within the region for x, right? So that's how you decide those bounds. And then y is going to go from the bottom of the region, which is y equals 1, the horizontal line, up to y equals x squared, which is the function that's bounding us. So we get this. And if you think about it, if you were going to do calc AB or calc 1 integral to find the area of this, you would definitely just integrate from 1 to 3 x squared minus 1. Like that's what you would do. Well, that translates into these bounds for the double integral. I really like using that. I recommend it. Not everyone does it, but it's a way to think about it that I think is a little clearer for some people. So this, we're going to go dy. The integral of e to the y is just e to the y. So we'll go 1 to 3. X is still there because it's just a constant. The integral of e to the y is e to the y, and we are going from y equals 1 to y equals x squared. And then fundamental theorem on this thing is going to give us x squared, the quantity, e to the x squared minus e to the 1. And that's a little weird. E to the 1 does not show up very often. But we're integrating with respect to x, so this is not a problem. I'm going to kind of distribute and make it into 2 integrals. Kind of an optional step, I would say, if you're very good at these. So for the first integral, there should be a 2 by the chain rule, so we're going to get 1/2 e to the x squared from 1 to 3. And then for the second one, we're going to get e over 2 x squared, which is one of the weirder integrals that you'll get. Just e is a base of an exponential makes sense to me, but e as a coefficient of a linear function is weird. So now fundamental theorem this thing, we're going to get e to the 9th minus e to the 1st. And then this one we'll get e over 2 and then 9 minus 1. And it cleans up, but it doesn't clean up much. I mean, like at the end of this, without a calculator, I'm not exactly sure what numerical value we're getting. But I'm getting 1/2 e to the 9th and then minus 9/2 e. So that is the final answer on that. I'm going to end this one here. I will be back in the next video to do the next page of the notes. And I'll see you there, and I hope you found this helpful.